Okay, day 2 of Unit 4 is called the derivative at a point. We're getting closer and closer to what we really want to find, and this unit is all about the special word derivative, which is a fancy word for slope or rate of change. So last class we talked about the average rate of change. We talked about this point here, this point here, and these values, and we came up with this formula. This is key. We're going to use this a lot. So f of x plus h minus f of x over h is the key to this unit. So we have another couple of examples. So my average rate of change, 2 plug in x plus h minus 5 minus the original function all over h. Distribute. My favorite step of getting things to cancel out. Has an h? No, it's got a buddy. Has an h? Yes, stays. Has an h? No, has a buddy. And now we have 2h over h, and my average rate of change is equal to 2, and that's an easy one because we knew this was a linear equation with a slope of 2. This one's a little bit harder. It's going to take more work because my average rate of change is going to equal to x plus h squared plus 5 x plus h minus 3 minus the original function over h. And I'm going to expand things out. You better know that x plus h squared is x squared plus 2xh plus h squared. Distribute the 5, subtract the 3, and then distribute the negative sign all over h. My favorite step is canceling everything in the numerator that does not have an h. X squared has a buddy, has an h, has an h. 5x has a buddy, has an h. Negative 3 has a buddy. If you don't get it to do that, where everything's canceled out, you did something wrong. So now I have 2xh plus h squared plus 5h over h, and I don't factor out the h. I realize that this 1h is cashing out 1h here, 1h here, and 1h here. So I get my average rate of change is 2x plus h plus 5. This is what we did last class, and something we're going to use a lot in this unit. So now we're going to do it at a specific number. Not just x, but x is equal to a, where a is some number. So I have to put a number in here. I have to put a number in here. So my steps are, first thing I'm going to do is figure out the y value when I use x equals a. I'm going to plug a plus h into the formula. I'm going to expand it and simplify it. So I'm finding the derivative, or the average rate of change, specifically at that point. So I'm going to move this up a little bit. So here's my function. Here's my x value. So I have to find f of 1 first. And when I do that, I get 1 squared plus 5 times 1 minus 3. I get a result of 3. So I have the point 1 comma 3, x comma y. So now when I do my average rate of change, I'm going to do f of 1 plus h minus f of 1 all over h. I have to plug 1 plus h in here. 1 plus h squared plus 5 times 1 plus h minus 3 minus the y value I got here, which was 3, all over h. I'm going to expand this out. Equals 1 plus h squared is 1 plus 2h plus h squared plus 5 plus 5h minus 3 minus 3 all over h. It's the same process as before. Anything that does not have an h should cancel out. 1 plus 5 is 6 minus 3 is minus 6. So these numbers do cancel out. I have 2h plus 5h is 7h plus h squared all over h. I can cancel out 1h here, and h here, and h here. So my average rate of change equals 7 plus h at x equals 1. That's what we're trying to do. Okay, the next problem, very similar to what we did before, just a different function. X still equals 1. So I plugged it in there, I got a y value of 4. So I have the 0.14, and I'm going to do this whole process of plugging in 1 plus h. So it's going to be 2, 1 plus h squared, minus 3, 1 plus h, plus 5, minus the original y value of 4, all over h. I'm going to expand this out. Equals, well, 1 plus h squared we just did earlier was 1 plus 2h plus h squared, so now it's going to be times 2. It's going to be 2 plus 4h plus 2h squared. Distribute that negative 3. And then I have all this all over h. And if I did this right, 2 minus 3 plus 5 minus 4 is 2 and 5 is 7. Minus 3 minus 4 is negative 7. They all cancel. So let's flip it over the numerator. 4h minus 3h is 1h plus 2h squared all over h. And I'm going to cancel again. These h's cancel, but it leaves a 1 left over. This cancels out one of these h's. So I get my average rate of change is equal to 1 plus 2h when x is equal to 1. That is the average rate of change. So we've done a couple of days of this whole average rate of change formula with f of x plus h minus f of x over h. We haven't talked about h too much. H is the difference between the 2 points A and B. So what happens if h becomes smaller? That means the letter B gets closer to point A. If you notice, every time as h gets closer to 0, B gets closer to point A. And if you notice, we have these secant line, secant line, secant line, secant line. And the whole idea is that what happens if h becomes 0? Then B is on top of point A. See? They're getting closer and closer and closer to the point where maybe I get it to the point where point B is on top of point A. And all these lines earlier, these are all secant lines, secant lines, secant lines. And then finally, where I get B is on top of A, I get something that is a instantaneous rate of change, not an average rate of change, and this becomes a tangent line. And that's what we're really looking at. And the slope of the curve at point A, the instantaneous rate of change, or the slope of the tangent line at slope of the curve at point A, is called the special word derivative. Okay? And that's what we're working on, finding derivatives. This whole unit, probably the next couple units, it's all about derivatives. And the idea is that math, we do have synonyms. So if I say any of these things, instantaneous rate of change, slope of the tangent line, slope of the curve, f prime of a, y prime, dy over dx, derivative, differential, these are all synonyms to the word derivative. Okay, this is read f prime, this is read y prime, that's not f y to the first or f to the first. dy over dx, well, let's see. Looks very similar to delta y over delta x. Delta being the Greek letter D. That's what we're working on. So the whole point is the derivative at point A can be interpreted as the slope of the curve at point A or the slope of the tangent line. Let's try some examples. So one way to figure this all out, a derivative, is saying, you know what, I still want to use my slope formula. I still want to use m equals change in y over change in x. But to use that formula, I need 2 points. So what we're going to do is to approximate the derivative by taking another point that is very, very, very close to the original point, so that h value, that distance between the 2 points, is very small. The smaller the h value, the better approximation I have for the derivative. So this is all calculator. Now, it's not exact. This is an approximate value, and that's what we're going to look at. So this is all calculator work. So I have a function here. I'm going to plug in the x value, and if I do f of 1, I get 1, so I have the point 1 comma 1. H is not the next number I'm plugging in. My new point will be the original x value plus the h. So I'm going to use my new value of 1.1, and I do f of 1.1. I plug that in the calculator. I get 1.21. So I have 1.1, 1.21, and I have 1 as the original. So what I want to do, here's my formula right here. It says f prime of a number. My number I'm using is 1 is equal to the second point minus the first point, so 1.21 minus 1 over the h value of 0.1, which is 0.21 over 0.1. So I get f prime of 1 is about 2.1. It's not exactly 2.1 because I didn't use just 1 point. I had to use 2 points, but it's pretty darn close. Let's go to the next. Well, I still have my point. I still have my 0.11, except now my new point I have is 1 plus 0.01, which is equal to 1.01. So now I have to do f of 1.01, and I plug it in the calculator. This is all calculator work. This is 1.0201. So here are my values that I have for x and y, and all I'm doing is y2 minus y1. So f prime of still 1, that is the original x value that does not change, is equal to 1.0201 minus the original x of 1 over the h value of 0.01, which is 0.0201 over 0.01. So f prime of 1 is about 2.01. Again, it's not exact, but it is close. And if you're seeing this, the smaller I make h, the better approximation that I have here. So my question is, do you see a trend? What is happening as h is going smaller? What do you think f prime of 1 actually is. Remember, these are not perfect. These are approximators. F prime of 1 is about 2.1 when I use h as 0.1, or f prime of 1 is equal to 2.01 when I use a smaller h. Well, I'm seeing a trend here. I'm seeing that I'm getting closer and closer and closer to f prime of 1 is equal to 2. And we'll learn more about that in the next few days. Okay, another example, I have a different function. This time I have the function 1 over x, but I'm still using x equal 1, so I have the original point 1, 1. When I do an h value, the h value is not the new x value. I have to add it to the original x value, so the new x value is 1.1. I plugged it into the function, and I got about 0.909. I know there's more decimals, but for right now we're okay. So f prime of 1 is equal to y2.909 minus y1 over the h, so negative 0.091 over 0.01. So f prime of 1 is equal to negative 0.91. This is what I got for the approximate derivative. Let me try a smaller h. Let's do the new h is equal to 1 plus 0.01, which is 1.01. So I have to do f of 1.01. I plug that in the calculator. I get 0.990099. And there's more decimals, I get it. So I'm using 1.01, 0.990099 as my points. So f prime of 1 is equal to 0.99099 minus 1 over 0.01, and that is equal to negative 0.009. Oop, I forgot another 0 here. Let me see. 0.009901 over 0.01. Let me clear that up a little bit. Let me put 2 zeros in there that are nice and neat. 0, 0. So f prime of 1 is about negative 0.9901. Again, it's an approximate derivative. It's not exact, but, excuse me. Do we see a trend here? I think I do. I think the trend is that f prime of 1 is actually equal to negative 1 if we follow this trend. Okay, ask questions in class, do your daily assessment. We're going to turn stuff in. Thank you for watching this video.